So welcome all, and today we will cover another lecture on the course Line Commutated and PWM Rectifiers. And today we will talk about Vienna Rectifier. So if you see here, we are in this week 10, and we are going to cover the Vienna Rectifier, the circuit topology and steady state analysis, right? And please note that we have already covered this NPC rectifier in the previous lecture, and this Vienna rectifier, as we will understand, is basically an extension of the NPC. More precisely, it is an extension of the TNPC. Okay, so let us first understand the application area of this Vienna rectifier. Vienna rectifier is a three-phase converter used for AC to DC applications, and it is always run as a rectifier. Okay, and it has found applications in telecom power supplies, UPS, EV charging, etc. And the power rating can be several tens of kilowatt. And Vienna rectifier uh, has been developed by a research team led by Professor Kohler in ETH Zurich, and they have published a lot of papers on this converter, and you can refer to some of these papers. The Vienna rectifier has the following features. Basically, it is a three-phase bridgeless boost PFC, and it is unidirectional, and it is highly efficient and compact. Okay, so we can say that this converter has been driven commercially. I mean, commercially it is available from several manufacturers, and the reason why it has been very popular is it is very efficient and compact. So many cases we have seen that Vienna rectifiers, at least at the academic scale, has been kind of like reported at several tens of kilowatt, but an efficiency of more than 98% with silicon carbide switches. So there are some prospects of this converter, and let us see how this converter functions, or how can we derive this converter. As we have told earlier that it is a boost PFC converter. Okay, so a boost converter can be a starting point to derive a Vienna rectifier. Okay, so this is a boost converter. Now, since we are going to interface the AC grid, so we can actually think of this boost converter. We can have another boost converter. So in this case, this is the plus. Okay, and here this is the minus side. Okay, as if like on the negative half of the AC cycle, we are having another boost converter with this circuit topology. Okay, so this is not the actual topology. Okay, please remember that we are trying to derive, and I am here showing you the thinking process, okay, behind the development of a circuit topology. It is not exactly the circuit topology that we are going to use. So we are thinking in this way. So so here we have this this plus, and this is the minus, so negative portion of the boost converter, and these arrows here indicate the charging and discharging that will happen to these two inductors. Okay, we know this phenomenon. Now let us try to get rid of these two inductors and try to get a single inductor, but now we have a AC input. Okay, so this is possible. Okay, you can see here that if I put an AC input here, this is where the AC input, and we have the inductor we have placed at in series with the AC input. We have the diodes here, like the one which we have shown, these two diodes here. Of course, the lower diode has been now reversed, but we have got the diodes working here. But now, instead of two switches, we have this single switch S here. Okay. Now, let us understand here. Remember that this current here must be AC. The inductor current must be AC, which means that the current will reverse its polarity. We are talking about a rectifier with unity power factor operation. Okay, so which means the current will be following the grid voltage and it will be alternating. So therefore, this current will reverse. So therefore, obviously, one can understand that this switch has to carry current in both the directions, right? Because you see, when in the positive half, the current will be like this and like this. And in the negative half, the current will be like this and the current will be like this. Okay, you can see here from if you analyze it. So therefore, we can say that this current here will be bidirectional in nature. Okay, the current here will be bidirectional in nature. This is the current which will flow through the switch. Now, what about the voltage which needs to be blocked by this switch? So when this diode is conducting, okay, we can see that this plus terminal will come here. Okay, so this is where it will come, right? And therefore, the V1 is more than V2. Okay, so under this condition, right? Now, in the other half of the AC cycle, right, this diode will be conducting and this diode will be off, of course. This diode will be conducting. When this diode conducts, what happens? You can see here, this becomes the plus terminal here, and this diode is connected to this point. In the lower diode is connected to this point. So under that condition, when this diode is conducting here, right? So let me give it in a different manner. When this diode is conducting, you can see this point's voltage, okay, is plus here because this plus voltage is coming at this point. This diode is conducting. So therefore, during that point, V2 is greater than V1. Okay, so which means that this switch S will experience at certain points of time V1 more than V2, and at certain other points, I mean in the positive half of the AC cycle, it will experience V1 more than V2. In the negative half of the AC cycle, it will experience V2 more than V1. So this means that, and also we have seen that from here, we have seen that the current must be bidirectional in the switch. So this indicates that we have to have a 4-quadrant switch here. Okay, so we must have 4-quadrant switch. The S must be a 4-quadrant switch. Okay, S must be a 4-quadrant switch. Now, this means, so there are several implementations of a 4-quadrant switch. Okay, 2 implementations we have shown here. So let me erase this part. So 2 implementations of the 4 quadrants. So this is one implementation and this is the other implementation. So this is what I have written, 2 possibilities for S. Okay, so both are possible. Okay, so let us now, therefore, so please keep this in mind that S here must be a bidirectional switch. Now let us extend this concept through a three-phase system. Okay, so here you can see along with the red, along with the black one, I have added the red phase and the blue phase. Okay, the same thing, but I have now superimposed this thing. Okay, so there are three sources and there are three four-quadrant switches, right? There are three inductors and six diodes, okay, which are present in this switch. And this circuit looks a little bit clumsy, okay? So much connections and it looks clumsy. So let us try to clear this circuit a little bit. Okay, so what the first step that we can do, you can see here that these three currents are coming here from the same point and going into the three phases. So this is where this connection is actually. And now what the first step in simplification is that in a three-phase system, the sum of the three-phase currents is zero in the neutral wire. Okay, so there was this connection was there connected to this point here, and we have now removed this connection. It is not needed. Okay, because we have the we have the sum of the three currents to be zero, right? So the first step we are doing is we remove the neutral point connection, and then we see whether we can further improve the circuit. One thing that we note here is, of course, that one thing that we can note here is that we have like three sets of these diodes in the rectifier format. Okay, this is the diode bridge, three-phase diode bridge rectifier. Okay, so when we see this one, we can then say, okay, let us draw it in this way. Okay, these are the three diodes, right, which we see here. Of course, we have the AC source and the inductors here, and here also the AC source and the inductor. Okay, and now we have drawn the diodes, and the middle point of this capacitors, here we see the middle point of this capacitor. This middle point is connected to the inductors at this point through these four quadrant switches. So here you can see this middle point of the capacitors are connected to the inductor points through these four quadrant switches, right? So this is how the converter looks like now, right? You have a three-phase AC, you have the filter, this inductors, and the three-phase diode bridge rectifier, four quadrant switches, three of them, and output DC port. Okay, so this is basically the one format of the Vienna rectifier. This format of this Vienna rectifier is actually quite popular. Okay, there is another format. I will show it in the next slide, but you can understand that this converter looks very familiar, and it is actually um, pretty straightforward because we have the diode bridge rectifiers here, inductors and AC, and in addition, we have these four quadrant switches present. Okay. Uh, Now, one thing that we can observe here is that these diodes D11 and D21 should block the full output DC voltage in A phase. So, for example, as I tell you that if this diode is conducting, okay, if this diode is conducting, then this diode has to block the entire DC bus, right? Because this plus point will come here, okay? And the minus point is as it is here. So therefore, if this upper diode is conducting, D21 has to block the full DC bus voltage, okay? Now, so this is one point where further modifications are possible, right? So what we can do if we want to further make modifications to have the same device rating, same voltage rating of VD by 2, we can introduce this 4-quadrant switch inside the leg of the converter. Okay, here you can see that this point is connected here and this point is connected to the middle here. Okay, so we have now introduced the 4-quadrant switch inside the one leg of the converter. What is the advantage? Now all switches here, all switches and diodes, everything have a rating of VD by 2. How is it? For example, now if you see that suppose this upper diode is conducting, then this and this is conducting, right? So then this plus point comes to here. Okay, and you can see that there are now two diodes present, right? Two diodes present to block this plus voltage, right? So therefore we can say that at any point of time, so the voltage rating of the this all the switches here have a voltage rating of VD by 2 in this case. Okay, so this is the second format of Vienna rectifier in which all the devices have the same voltage rating, which is equal to VD by 2. However, this second form has some disadvantage as compared to the first form. Okay, what is the disadvantage is that at any point of time you can see at least two devices, and in some cases three devices are conducting. For example, you take this one. Suppose when you get the plus voltage, then you see there are two devices conducting here, right? So this is how the devices will be conducting. Whereas sometimes three devices will be conducting, right? Suppose under this condition, okay, there are three devices conducting. The way I am drawing now, the orange waveform, three devices are conducting. So in this converter, one disadvantage is, in particular, when you have this plus and the minus, you have two devices in series connection, which means the conduction loss will increase. On the other hand, if you see the previous form, in particular, suppose here, when the plus is taken or the plus, suppose this plus voltage is coming, right? Then only one device is conducting. Okay, only one. Okay, and then you get the plus. Okay, so this second format has some advantage, but it has some disadvantage also, right? So both these forms, both the two circuits are actually used. Okay, this one and this one both are used. In fact, this one, several commercial applications actually exist. Okay, and we will continue with this one. We will analyze this format a little bit more in details. But the analysis is absolutely identical to this format also. Okay, only the conduction losses will change and the path of the conduction will change. So the analysis, whatever we will do, is equally applicable to both the circuit formats. Okay. Okay. Yes. One of the things, so this, suppose we take this format of the converter and let us stop a little bit and try to see whether we already know this converter. Okay. And in fact, this converter, the one in this format here, this converter has a lot of similarity with the T-type NPC. We have seen this T-type NPC in the previous lecture. I have shown this T-type NPC here. Okay. Remember, initially NPC was derived And when NPC was derived, people had realized that this T-type NPC is also possible, but they could not, that did not get popular because 30 or 40 years back, the devices were not that powerful. Only IGBTs where their silicon carbide MOSFET had not come in the market. Okay. Now, if you see here, let us see the T-type NPC and this Vienna rectifier, this format. Okay, this circuit topology. Okay. In this case, so here is the AC grid. I have drawn it on the one from the left to right and another from right to left, just to show you that the same circuit looks different, okay, when you look from different perspective. So here you can see there is a DC link and there is a midpoint, and there is a DC link and there is a midpoint, and then there is a 4-quadrant switch, and here is a 4-quadrant switch. It's the same. In this case, the 4-quadrant switch has been made with IGBTs, with the series connection, okay, with anti-parallel diodes. Here it is being made with MOSFET with uh, this kind of a 4-switch, this configuration. Now, after that, what we find here is that we have these two diodes, okay, in phase A. If I compare the phase A of this NPC, you see here, we had this switch, but now suppose I remove these IGBTs here, right? What do we get? We get the same Vienna rectifier, okay? So you can see here that the T-type NPC, if you remove these controllable switches, S1 and S2, basically you land up in the uh, you land up in the Vienna rectifier. Okay, right? So remember, a T-type NPC is a bidirectional converter, which means the power can flow both directions because we have the controllable switches here. There are controllable switches here, right? And that is why this bidirectional power was possible, because we had IGBTs, or if I use MOSFETs in place of IGBTs, so we have controllable switches here. So that's why the power can flow both directions. On the other hand, in Vienna rectifier, we have diodes here. So the power can only flow in this direction. It cannot go back. So this is a unidirectional rectifier. So this is unidirectional. Okay, so that's what I am saying. Bidirectional PFC in TNPC now becomes unidirectional PFC. Okay, so this is unidirectional, whereas this is bidirectional. Okay, so this is one important observation. And here also, another thing that you can see here is that IGBTs have been replaced with silicon carbide diodes and MOSFETs. Okay, so here you can see that these are silicon carbide MOSFETs. Even these diodes are silicon carbide diodes, right? Um, so because they are continuously switching. Okay, we will show the analysis of the switching, but they're continuously switching. So one diode and switch is switched in the positive half, and one diode and switch is switched in the negative half of the AC cycle. So generally, these are all made with silicon carbide because these are more modern converters. Okay, but if you understand the T-type NPC very well, you can as well find out the operation of the Vienna rectifier. Okay. Yeah. So what are the features? So let us now come back to the Vienna rectifier and see what are the features. It's a three-phase converter. It is three-level. Why it is three-level? You can see here that this is the pole voltage. This is the pole voltage of the converter. When you turn on this diode, okay, then you get this plus voltage at this point, right? Similarly, when you turn on this diode, you get the minus voltage. right, at this pole of the converter, right? And then if you turn on the 4-quadrant switch, okay, this 4-quadrant switch, if you turn on this 4-quadrant switch, then you get 0 or the midpoint, right? So this is a 3-level converter. In this pole voltage, you can get plus, 0 or minus, just like an NPC, okay? Exactly same. However, here something else will happen. I will talk about it sometime later. Also, you understand that this is a 3-phase boost converter that steps up the AC voltage to DC output while enforcing sinusoidal input current. Okay, um, this statement, okay, a boost converter, because is something which is depends on in which direction you look into the converter. Okay, this is very interesting. As I told you, we have seen this T-type NPC converter. Okay, when we discussed the T-type NPC, we were always looking from this side to this side. Okay, let me draw it here. Okay, let me clear this one. This boost converter and buck converter, this is something which is very interesting to observe. You see, the DC link is here is the DC link. This DC link is more than the peak of the AC voltage here. So what you see here is it's a boosting operation. That is how we have done the analysis. Okay, we said that this is an inductor. We will charge it up and we will discharge it. Okay, something like this, where charging and discharging will happen with the boost converter. Okay, so therefore we say this is a boost converter because we are looking from AC to DC side. On the other hand, I told you that this has very much similarity with the NPC, T-type NPC. And we have studied the T-type NPC also when we were talking about inverters, okay, DC to AC converters. Now, suppose you look from this side, okay, you look from the DC side, then what happens? So this entire converter here is basically like a modified version of NPC. So if you look from the right hand side, this becomes a buck converter. Okay, and here comes the output voltage, which by sinusoidal PWM, we have the modulation index M, right? Okay, and that M can be controlled. I mean, that the modulation index M is always less than 1. Okay, so looking from the right hand side, this becomes a buck converter, whereas looking from the left hand side, this becomes a boost converter. Okay, so looking from the buck side, you can see that this is a T-type NPC. Okay, whereas looking from the left side, you can see that this is a Vienna rectifier or boost PFC. Okay, so it all depends on which direction you are looking at. Both of them actually lead to the same operation and same circuit, and we have already covered both of them. Okay, we have covered boost PFC. We have also covered NPC and T-type NPC or voltage source converters, 3-phase 2-level voltage source converter. We have covered both of them. So we now see that we actually know all the operation of the Vienna rectifier. Okay, we have seen the left-hand side uh, and we have also seen the analysis from the right-hand side. Okay, so basically we will then therefore uh, reiterate what we already know, and we will analyze this converter from the knowledge that we already have. Okay, now let us go a little bit more in depth. We know already how will we operate. Okay, so, but let us study once more. Okay, how the charging and discharging will happen, although we know how it will going to happen. So in the positive half cycle, I greater than 0, okay, so we are now analyzing from the left to right. Okay, so we will analyze like a boost PFC. Okay, this is our left to right analysis. So therefore, boost PFC means we'll charge the inductor once and we will discharge it once more. Okay, so when you have, so how will you charge the inductor? So you will turn on this switch. Okay, suppose I is greater than 0, we are in the, remember this current here has to, is will going to be sinusoidal. Okay, and will be in phase with the voltage. Okay, it's a rectifier, almost unity power factor rectifier. So this current will be in phase with the voltage. So what we will see here is that during this positive half cycle, right, we will sometime we will turn on this switch, the 4-quadrant switch, and so the inductor will charge up. And how will you discharge, right? So the current will go from here, and so you will turn off this switch and the current will go like this. Okay, so this is how, this means that this diode and this 4-quadrant switch, this diode and this 4-quadrant switch is going to be completely working when the A phase current is positive. I mean, in the positive half of the A phase voltage or current, the upper diode in A phase and this 4-quadrant switch are continuously getting on and off, thereby causing charging and discharging, right? Of course, as I told you, this circuit is not getting complete, and the circuit will get complete, for example, through the other phase. Okay, remember that. Okay, this is how the circuit gets complete. It is like same like a 3-phase VSC. Okay, the circuit gets complete only through the other phase. Okay, so this is how the circuit gets complete and the current flows. Now, when the current is less than 0, okay, when in the A phase uh, current, now we are talking about this area, okay, in the negative half cycle, the current polarity is reversed. So now the current will flow like this way. Okay, so then who will conduct? In fact, we will see that again the charging and discharging will happen, but now this diode will conduct for some time, and this way the current will flow in this one. Okay, so therefore charging and discharging can be accomplished, right? So here you can see sometimes the inductor will get charged and sometimes the inductor will get discharged. Okay, the current is flowing in this way, right? So basically we see that if we look it as from the perspective of a boost PFC, we see that the inductor current can be charged or discharged in the positive half cycle, positive half AC cycle, and negative half of AC cycle. And we can, we can do this job. One more thing that we must emphasize is, like in an NPC, we are basically accessing the midpoint of the DC link capacitor, right? So we will experience a midpoint voltage fluctuation like a 3-level NPC. Okay, this is going to happen because the current is flowing in or out of the midpoint voltage. Okay. Okay. So we get 3 levels of voltage at the pole of the converter, like we have shown, plus, 0, and minus. Okay. So this is summarized in this table. So when the MOSFET is on, UAM is 0 and the inductor energy increases. When it is off, then it is decreasing. And so these are the 3 levels of voltages which are possible at this UAM. UAM means this is the A point and this is the M point here. Okay, so this UAM voltage will be 0 plus or minus. Okay, and for that, so note that, okay, note that because of this UPF operation, we are at UPF operation. In the positive half cycle of the AC voltage, we will only use plus and zero. So these two will only be used during positive half of AC cycle. And these two will be used in the negative half of the AC cycle. We are working at UPF. Okay. This condition will get violated if we do not work at UPF, if there is a lagging or leading current. Okay. And that's when the rectifiers, the diodes have to be changed with a control switch. Okay, but since we are operating at UPF for the Vienna rectifier, so therefore we can say that this 0 and VDC will be coming in the positive half of the AC cycle, and in the negative half of the AC cycle we will get 0 and minus VDC by 2. So we can say that the output voltage will be something like this. So in the positive half of the AC cycle, so this is the positive half of the AC cycle. So we will do like this. Okay, 0 and VDC by 2. Okay, and in the negative half of the AC cycle, like this, we will get 0 and minus VDC by 2. Right? So the AC waveform, okay, the fundamental component of the AC waveform, this is very known to us. We have done this thing several times while we were doing sinusoidal PWM. So if we do like this, our AC is basically embedded in this series of pulses. Okay, and that pulse width will by changing the pulse width, we can change the magnitude of the AC voltage. Right. So this is also, it's very familiar to us. Okay, we have done this several times, and we can now see that Vienna rectifier has very much similarity in operation from the uh, yeah, looking from the boost PFC side or looking as an inverter side. Okay, yeah. So this is what we have said. The analysis can be done either from the DC link side or the AC grid side. Okay, so looking from the DC link side, suppose you look from this side, what happens, as I had shown, this point's voltage becomes a series of pulses like this. Okay, it is a series of pulses like this. And okay, and therefore we can make it a sinusoidal controllable AC voltage source, right? So what? So if you can make this one, then this is a sinusoidal controllable AC voltage source like sinusoidal PWM. And if we do that, then the whole of this Vienna rectifier will become something like as a VAM, okay, controllable AC voltage source, right? Because the fundamental component of this pole voltage is shaped in a sinusoidal waveform through an appropriate PWM script, okay? So the rectifier voltage is controllable both magnitude and phase wise. So you can actually change the so basically this is a controllable voltage source. So we have seen this several places. I can change the current. Okay, of course I will make the current at unity power factor, right? Uh, but I can change the magnitude of this current. Okay, so yeah, so we can do it like this way. For example, at steady state, this is the AC voltage from the at the pole. Okay, the AC fundamental component of the AC voltage, and this is the fundamental component of the grid voltage. And you have IA, RA, and J omega IA LA drop across the inductor. So if your grid voltage is here, you will make the current at unity power factor. And of course, you have IA, RA drop and JIA XA drop, which will become the IZ drop here. And so this VAM, this is this VAM voltage, you can manipulate. Okay, you can manipulate this voltage, keeping the current and the voltage always at unity power factor. Okay, and so you can control the active power from the grid to the converter. Okay, so this is the analysis when we talk this from the AC point of view. Now you can also do the same analysis. You will come to the same conclusion. Okay. If you do the analysis thinking it as a boost PFC. Okay. So the analysis can also be done from the AC grid side. Okay. And it follows exactly how a boost PFC operates. Okay. So then we will see, okay, we have this converter. This is the inductor. Sometimes it is getting charged and sometimes it is getting discharged. One through switch and one through the diode, right? So the duty ratio, again, we have, so you can recall how we have operated the boost PFC in few lectures before. So the duty ratio is something like this, okay? 1 minus VGA, the grid voltage, divided by VDC, which is like Vm mod of sine omega t. And we have also designed the inductor based on this maximum current at the peak of the AC cycle. And then the capital D was 1 minus V max divided by VDC. And we found that the L can be designed in this way: Vm into D by delta L by Fs, where delta L is the peak to peak ripple. Okay, so this current here, if you see this current is sinusoidal, but there is a delta IL, um, delta L peak to peak, which comes from the boost PFC operation, right? So this is exactly, we know all of this, right? So the analysis of the Vienna rectifier already follows what we know. Okay, so now we can say that how we do the current control. Now things will become very simple for us. So how do you do the current control? Okay, so you can use several, so you have to basically control this current IA, IB, IC in sinusoidal fashion and at unity power factor. You can use several modulation schemes like hysteresis PWM, sinusoidal PWM. Okay, what do you do in hysteresis? You control the current within the two hysteresis bands. Okay, so for example, this is the current Ix star. The star means the reference current, the green colored, and Ix is the actual current. Okay, so you will control the current in such a way. So of course, it is going on and off the switch, and it is within this band. Of course, this diagram is exaggerated. Actually, the diagram looks like this. So this is the actual current, and the switching frequency is much faster than this. So actually, it looks like this. Basically, it is like this. Okay. So the switching frequency can be like 50 kilohertz or 60 kilohertz, something like that. So it is very fine like this. So it is not the way we have shown it here for exaggeration, right? So therefore you can control the current within these two bands, okay, plus H and minus H, okay. So we have shown it here, how the current. So when the S is on in the positive half of the AC cycle, the inductor is charging up here, and when you so the inductor, with this the inductor will charge up, and when you turn off the switch, the inductor will discharge. So this is the place when the inductor discharges, okay, and you can follow the analysis that we have shown. The switch is turned off, so current decreases and the inductor discharges. Okay, so the current goes down to the lower band and the switch is again turned on. So this is the principle of the hysteresis current control. And similarly, in the negative half cycle also, we will use the lower diode and the switch of the A phase or any other phase, and you will make it like upper, you will again do it within a band. Okay, and the process will continue. Okay, now, yeah, so when you do this one, as you can see, we have tried to draw the switching states. And here you can see that this is the current here, okay, and how the switch is functioning. Okay, this is the MOSFET. Okay, this is the MOSFET, which is the switching pulses to the MOSFET. And therefore, in this case, the actual voltage VXM, right? this VXM voltage will be looking like this. You can see here it is going from VDC by 2 to minus VDC by 2, but in between you have the zero states. Okay, so this is how the switching will look like. Of course, this switching has been made with a switching with this kind of a hysteresis band where the switching frequency is very small. Actually, the switching frequency is much higher than what has been shown in this figure. Okay, so this is how the pole voltage will look like. And we know that this pole voltage is nothing but a 3-level pole voltage waveform output. Okay, fine. The last part of our analysis concerns the midpoint voltage. We have seen this also previously in NPC also, that we are going to access the midpoint of this voltage. Okay, and there's a series connected capacitor, and as soon as we are going to access this midpoint, some current will flow in or out of this midpoint, and this will lead to different voltages of the capacitor. All right, and this is a phenomenon which we have already seen in NPC. It will also happen here, and it's exactly same film. So I have shown it here, okay, with two cases. Like suppose you have this plus minus zero combination, which means A phase is connected to plus. You can see here A phase is connected to plus and B phase is connected to minus. So B phase is connected to minus here, and then zero. C phase is connected to zero. Okay, C phase is connected to the midpoint. So then what is the midpoint current? IM. This is the current IM which we are talking about. What is IM? IM is equal to IC. Okay, in this case, I have taken the other Vienna rectifier form 2, circuit 2. Okay, the analysis is similar with circuit 1 also. I uh, just wanted to have the second form and analyze it. Okay, so Im is equal to IC here. Okay. Now, if you take the other case, suppose you take 0 minus 0. So which means that these zeros are getting accessed, right? And so Im will be equal to Ia plus IC, which will be equal to minus IB. Okay, so you can see here that if you use these two switching states, okay, then the midpoint voltage, the current which is flowing through the midpoint voltage is different. And so the midpoint voltage will fluctuate. Now we have to keep the capacitor voltages equal. So the midpoint voltage has to be half the DC link voltage. So what do we do here? We apply something which we also know from previously. Remember that in NPC, when we wanted to change the midpoint voltages, what we did, we had this T0 time, we had changed to T0 by 2 and T0 by 2 plus delta T and T0 by 2 minus delta T, right? That's what we did. So basically, if you have these three reference waveforms, if you shift all of them together, okay, if you shift all the three waveforms, reference waveforms together, the T1 and T2 does not change. So the effective voltage remains the same. And but the delta T, okay, the T0 times get changes. So instead of T0 by 2, like in space vector PWM, this becomes T0 by 2 plus delta T. Another one becomes T0 by 2 minus delta T, right? So it will cause the capacitor voltages to change depending on how much delta T and how much is the instantaneous current. Okay, remember, we can recall that one. Exactly similarly, here we can do the same thing, but now we can introduce a zero sequence current. Okay, it's the same principle, right? This zero sequence current, we add it to the three reference waveforms. The three reference waveforms are balanced, IA star, IB star, IC star. But now we will add this I0 star to the three reference currents, okay? And it will change to I0 star. And this additional current, okay, through a closed loop control, we will be able to control the DC bus midpoint voltage. Okay, so how do we get this one? So basically, uh, we will get the two DC link voltages. Okay, so these two DC links voltages, we give the name UC1 and UC2. Okay, plus these two voltages, and we see a difference of these voltages. If they're at perfectly midpoint, then this voltage will become zero. We will not need I0 star. But if it is not zero, some value will come here and I0 star will be generated. Okay, this so this voltage deviation UC1 minus UC2 is fed to a PI controller, which will set up this reference current I0 star. This will be added to the main control loop. So how does this look like? You see here UC1 and UC2, and this goes to the PI controller, and this generates the I0 star. And how do we get the actual currents IA star, IB star, IC star? In order to do that, we first get this voltages, DC link voltages, and if there is any error in the DC link voltages, that sets up the magnitude of the current needed. Okay, how does this happen? So if the DC link is falling, okay, if the DC link is falling, then we will get a positive delta VTC error. Okay, VDC is falling, suppose this is falling, okay, and we have set a voltage reference. So then delta VDC will be positive, and therefore we need more power, more active power from the grid, and hence I peak will increase. On the other hand, if VDC is if it's rising, if VDC is actually rising, what will happen? This it will go more than VDC star, and therefore delta VDC will become lesser and I peak will go down. So therefore, by sensing the DC bus voltage, we will be able to see how much is the peak current. So which means that this is the current. This peak can go up or down, okay, depending on the power requirement. This peak will go up and down. Okay, so then we can control how much is the power flow happening. And what is the shape of this current? How we need to have a sinusoidal shape of current in phase with the voltage. So we will sense the grid voltage here. We'll get the template of the grid voltage VGX. Okay, X equal to ABC. We'll get the template, multiply with them. So I will get a sinusoidal reference, okay, of this current. To this, we will add the I0 star, I naught star, which is coming from the capacitor, and then actual currents are sensed, and this is the hysteresis controller, which will give the pulses to the 3-4 quadrant switch MOSFETs. Okay, and we will have this in the rectifier. So this is a pretty simple and quite effective way of controlling the Vienna rectifier. Okay, so with this we come to the end of this lecture, and here we see that it is a very promising three-phase rectifier. But remember, it is a rectifier. Okay, it cannot exchange energy both ways. Okay, if you want to do that, then you have to use a T-type NPC. Okay, um, but this is noted for very high power density and efficiency. Okay, so you can say that it is an extension of the T-type NPC, and it has found a lot of applications like in EV charging, telecom rectifiers. Okay, in particular this telecom rectifier, there are lot of commercially also produced by different manufacturers. You can search in the internet. Telecom rectifier, Vienna rectifiers are frequently used. But please understand that we are now in a position in the course where we understand the different types of converters and how they can be suited. Remember, you may find it a little bit overwhelming initially that there are so many converters. Okay, how do I know which converter to use at what point? Okay, and this question is not very easy to answer. Okay, so it's true that there are, for any application, there are different types of converters available, but it will depend on what is the voltage level, what is the power level, like that. Okay, and what is our targeted efficiency, what is the size at which, and of course, the most, or probably the most important thing is what is the cost of the converter. So all these factors will lead us to one converter out of many possible choices. So we can understand that we have a good amount of choices, or there are many types of converters which are available in the market and in the also academic literatures, and we have to choose depending on these factors. So with this, we conclude the Vienna rectifier discussion.